Tonight, we follow the story of the diamond planet, 55 Cancri E, a world so extreme that even rock behaves differently. Once imagined as a place of immense value, it reveals something far more unusual, a planet where familiar materials exist beyond usefulness. Welcome to the Orbit for Sleep channel. Science moves slowly, quietly, and without urgency. Let us follow the orbit of science and drift gently towards sleep. You arrive at a world that does not resemble any familiar planet. 55 Cancri E moves extremely close to its star, completing a full orbit in less than one Earth day. From this distance, the surface never cools. Light from the star presses constantly against the planet, heating it to temperatures where rock does not remain solid, but behaves more like a slow, glowing liquid. As you settle into this scene, the scale becomes clear. The planet is slightly larger than Earth, yet far denser. Gravity feels heavier, as if every step would require more effort. There is no blue sky, no clouds shaped by water. Instead, heat dominates everything. Vast regions of the surface are thought to be covered by molten rock, forming what scientists describe as lava oceans. These are not rare eruptions, but stable, long-lasting features shaped by extreme temperature and pressure. The idea that brings attention to this planet is its unusual composition. Observations suggest that 55 Cancri E formed in an environment rich in carbon. On Earth, carbon appears in living tissue, fossil fuels, and thin layers of graphite inside pencils. On this planet, carbon may exist on a planetary scale. Under immense pressure, carbon atoms can arrange into crystal structures. This is the same process that forms diamonds deep within Earth, but here it may occur across vast regions of the interior. This does not mean the planet is a single, flawless gemstone. Instead, scientists describe layers where carbon-rich material, graphite, and diamond-like structures could exist beneath the surface. These conclusions come from measurements of mass, radius, and the way the planet blocks starlight as it passes in front of its star. By combining these clues, astronomers build models of what lies below the surface, much like estimating the contents of a sealed box by its weight and shape. The phrase, "worth more than Earth," comes from applying human ideas of value to a place where those ideas no longer function. Diamonds are valuable on Earth because they are rare, difficult to obtain, and culturally meaningful. On 55 Cancri E, abundance removes meaning. Even if diamonds are present, they exist in an environment where nothing can be held, mined, or used. Heat erases usefulness. Pressure reshapes everything. As the planet continues its rapid orbit, it offers a quiet lesson. Material wealth depends entirely on context. In one environment, carbon becomes a symbol of permanence and desire. In another, it becomes just another component of a hostile, uninhabitable world. The planet remains, glowing and silent, unconcerned with the values projected onto it from far away. 55 Cancri E is often introduced through a single striking idea, but the planet itself is more complex than any headline suggests. It belongs to a category known as super-Earths. These are planets larger than Earth, yet smaller than gas giants like Neptune. This size range allows for rocky surfaces, but also permits internal pressures far beyond what Earth experiences. The planet's mass is about 8 times that of Earth, while its radius is less than twice as large. This combination tells scientists that 55 Cancri E is unusually dense. Density matters because it offers clues about composition. A planet made mostly of gas would be lighter for its size. A planet rich in rock metal or carbon-based material becomes heavier. From this simple comparison, astronomers infer that 55 Cancri e is dominated by solid matter rather than thick atmospheres. Its orbit defines much of its character. The planet circles its star at a distance far closer than Mercury is to the Sun. One full orbit takes less than 18 hours. This extreme proximity exposes the surface to relentless radiation and heat. Over time, the planet became tightly locked, meaning one side constantly faces the star, while the other remains in permanent darkness. This locked rotation removes the familiar rhythm of day and night. Observations made using space telescopes reveal that the planet does not retain a stable, Earth-like atmosphere. Any gases released from the surface are quickly heated and stripped away by stellar radiation. Instead of clouds or weather systems, scientists expect a thin envelope of vaporized rock. Elements such as sodium, silicon monoxide, and oxygen may briefly exist above the surface before dispersing into space. Understanding 55 Cancri e requires separating what is known from what is inferred. Astronomers cannot see the surface directly. They rely on precise measurements of light, gravity, and motion. When the planet passes in front of its star, the starlight dims slightly. When it moves behind the star, the combined light changes again. These small variations allow researchers to estimate surface temperature and reflectivity. Together, these observations describe a world that is solid, compact, and extreme. It is not a jewel floating in space, but a dense, overheated planet shaped by proximity and pressure. Its true identity lies not in its nickname, but in the physical processes that govern its structure and behavior. The story of 55 Cancri e begins with careful measurement rather than dramatic imagery. The planet was identified through its effect on its parent star. As it orbits, its gravity causes the star to move slightly back and forth. This motion, detected through precise shifts in starlight, allowed astronomers to calculate the planet's mass. Later observations showed the planet passing directly in front of the star, briefly reducing the star's brightness. From this transit, scientists measured the planet's size. Mass and radius together form a powerful pair of clues. When combined, they reveal density. For 55 Cancri e, the numbers pointed to a world far denser than Earth. This immediately ruled out a gas-dominated planet. What remained was a solid body with an unusual internal makeup. At this stage, scientists turned to models of planetary formation to explain how such density could arise. The host star, 55 Cancri, was found to contain a higher ratio of carbon relative to oxygen compared to the Sun. This detail matters because planets form from the same disk of material as their star. In regions where carbon is abundant and oxygen is limited, carbon bonds with itself rather than forming silicate minerals. This chemical environment favors carbon-rich solids instead of the rocks common on Earth. Using this information, researchers simulated different internal compositions. Traditional Earth-like models could not match the observed density. When carbon-rich layers were introduced, including graphite and diamond-like structures under pressure, the models aligned more closely with the data. These are not direct observations of diamonds, but logical outcomes of known physics applied to extreme conditions. Additional evidence came from infrared measurements. Space-based telescopes observed the planet's thermal emission as it moved behind its star. The amount of heat released suggested a surface capable of storing and radiating energy efficiently, consistent with a rocky or carbon-rich surface rather than reflective gas clouds. The discovery of 55 Cancri's unusual composition did not happen all at once. It emerged gradually through repeated measurements, improved instruments, and refined models. Each step reduced uncertainty, replacing speculation with constraint. What remains is a portrait shaped by gravity, light, chemistry, and patience. The planet's reputation may sound extravagant, but its understanding is built from quiet, methodical science. The description of 55 Cancri as a world worth more than Earth originates from a familiar habit. Human societies often translate unfamiliar objects into economic terms. Gold, oil, and diamonds gain meaning through scarcity and usefulness. When astronomers suggested that large portions of this planet could contain diamond-like material, the comparison followed naturally. On Earth, diamonds form deep underground, where carbon experiences intense pressure and heat over long periods of time. They are valuable because they are rare, difficult to extract, and embedded in human culture as symbols of durability and status. A single gemstone can represent years of labor and geological time. This logic, however, depends entirely on an environment where diamonds are uncommon and accessible. On 55 Cancri, the conditions are fundamentally different. The planet's interior pressure is far greater than Earth's, and its chemical makeup favors carbon-rich compounds. Under such conditions, carbon does not need exceptional circumstances to crystallize. It follows known physical rules and organizes into dense structures whenever pressure allows. Abundance replaces rarity. Even if vast regions of diamond-like material exist beneath the surface, their presence carries no practical meaning. The surface temperature remains high enough to melt rock. Any attempt to approach the planet would face extreme radiation, unstable vaporized rock atmospheres, and crushing gravity. In everyday terms, it resembles owning a house made entirely of gold that sits inside an active volcano. The material itself remains valuable only in theory. This comparison highlights a deeper misunderstanding. Value is not an intrinsic property of matter. It emerges from context, need, and limitation. Oxygen is abundant on Earth and essential to life, yet rarely considered valuable. In deep space, oxygen becomes precious because it is scarce and difficult to obtain. The same shift applies to carbon and diamonds. By labeling 55 Cancri as more valuable than Earth, observers project terrestrial priorities onto an alien environment. The planet quietly resists this framing. Its significance lies not in hypothetical wealth, but in what it reveals about planetary diversity. It shows that the universe produces worlds where familiar materials lose their meaning, reminding us that value is a local concept shaped by circumstance rather than substance. The environment of 55 Cancri is defined by extremes that leave little room for variation. Its close orbit places it under constant stellar influence, where energy arrives faster than it can dissipate. Surface temperatures are estimated to exceed 2,000 degrees, high enough to melt most known rock types. In this setting, solid ground behaves less like land and more like a slow-moving fluid. The planet's rotation is locked to its star. One hemisphere remains permanently exposed to intense radiation, while the opposite side stays in continuous darkness. This arrangement removes the gradual transitions familiar on Earth. There is no sunrise to ease temperature change, no night to allow cooling. Instead, energy builds and remains trapped, shaping the surface over long periods of time. Models suggest that vast lava oceans dominate the dayside. These are not isolated pools, but extended regions of molten silicate material. Heat drives constant circulation within these molten layers, redistributing energy across the surface. In everyday terms, it resembles a pot of thick liquid kept on high heat, where motion never fully stops. Above the surface, the atmosphere behaves unlike any stable system. Traditional gases struggle to persist. Instead, elements released from the molten ground briefly form a thin envelope of vaporized rock. Sodium and silicon-based compounds may glow faintly before being stripped away by stellar radiation. This process repeats continuously, creating an atmosphere that is temporary rather than permanent. Gravity adds another layer to the environment. With a mass several times greater than Earth's, the planet exerts stronger pull. Any material lifted from the surface requires more energy to escape, yet intense radiation works against this force. The result is a delicate balance between retention and loss, maintained only under extreme conditions. Together, these factors produce a world where stability exists without comfort. The planet does not erupt violently, nor does it calm into equilibrium. It persists in a steady state of heat, pressure, and motion. This environment defines 55 Cancri more accurately than any nickname. It is a place shaped entirely by proximity, physics, and relentless energy, offering a clear conclusion to what kind of world it truly is. Beneath the surface of 55 Cancri, the planet's true uniqueness becomes clearer. While its exterior is shaped by heat and radiation, its interior is governed by pressure. The mass of the planet compresses material inward with far greater force than Earth's gravity ever could. As depth increases, familiar materials are pushed into unfamiliar states. On Earth, rocky planets are structured around silicate minerals and iron cores. These materials dominate because oxygen is abundant during formation. In the region where 55 Cancri formed, the chemical balance was different. Carbon was plentiful, while oxygen was relatively limited. This altered the building blocks available during the planet's earliest stages. As material accumulated, carbon bonded with itself rather than forming silicates. Under increasing pressure, carbon-rich layers were driven deeper into the planet. At shallow depths, carbon may exist as graphite, similar to the soft material used in pencils. Deeper down, pressure forces carbon atoms into tighter arrangements. In everyday terms, this resembles stacking identical objects so tightly that they snap into a rigid, ordered pattern. This is the physical pathway through which diamond-like structures can form. Surrounding these layers, scientists expect exotic mantles composed of dense, carbon-bearing minerals mixed with molten rock. Unlike Earth's mantle, which slowly convects over millions of years, heat within 55 Cancri may drive faster, more continuous motion. This internal activity helps maintain surface lava oceans and contributes to the planet's extreme thermal balance. At the center, the core is likely dominated by heavy elements such as iron, though its exact size remains uncertain. Models allow for a range of possibilities, but all suggest compression far beyond terrestrial experience. Every layer presses downward, creating a planet where structure is defined less by composition alone and more by relentless force. This internal architecture explains why the planet behaves as it does at the surface. Lava flows persist, heat remains trapped, carbon transforms under pressure. The interior of 55 Cancri is not a treasure vault, but a system shaped by physics, acting without interruption. It is a reminder that planetary structure emerges from conditions, not intention, and that even familiar elements take on new identities deep within an alien world. Inside 55 Cancri E, pressure does not simply increase with depth, it transforms matter step by step. Scientists describe this interior not as a single material, but as a sequence of layers, each shaped by temperature, chemistry, and force. These layers are theoretical, built from models that follow known physical laws under extreme conditions. Near the upper interior, carbon-rich material may exist in forms similar to graphite. On Earth, graphite is soft and slippery, used in pencils because its atomic layers slide easily over one another. In this region of the planet, heat remains intense, but pressure has not yet forced carbon into its most rigid state. The material stays dark, dense, and conductive. Deeper inside, pressure rises rapidly. Carbon atoms are pushed so closely together that their loose layered structure can no longer remain stable. The atoms reorganize into tightly bonded, three-dimensional networks. This transition marks the point where diamond-like structures become favorable. It is not a sudden boundary, but a gradual shift driven by depth and force. These diamond-rich regions are not expected to be clear gemstones. Instead, they would resemble massive, opaque, crystalline layers mixed with other minerals. Impurities, fractures, and extreme heat prevent the formation of transparent crystals. In everyday terms, it is closer to compressed industrial diamond than jewelry. Below these carbon layers, models suggest a mantle composed of molten and semi-molten material. This mantle may contain exotic compounds unfamiliar on Earth, formed from carbon, silicon, and metals interacting under high temperature. Motion within this layer is driven by heat escaping from the core, causing slow but continuous circulation. Each layer influences the others. Heat from below affects carbon stability above. Pressure from above reshapes the mantle beneath. Together, they form an interior that behaves as a connected system rather than isolated zones. In 55 Cancri E, structure is not static. It is maintained by balance between compression and motion, showing how familiar elements reorganize when placed under conditions far beyond those found on Earth. On 55 Cancri E, the boundary between solid ground and flowing material becomes difficult to define. The planet's surface is heated beyond the melting point of most rocks, allowing vast regions to exist in a molten state. These lava oceans are not brief events caused by eruptions. They are persistent features maintained by constant stellar energy. Rock behaves differently at extreme temperatures. Minerals that remain rigid on Earth soften, melt, and flow when exposed to sustained heat. On this planet, silicate rock can move slowly, like thick liquid. The surface does not crack and cool between cycles. It stays warm enough for motion to continue over long periods of time. The day side of the planet receives uninterrupted radiation. Energy accumulates faster than it can escape, driving convection within molten layers. Hot material rises, cooler material sinks, creating slow circulation across the surface. In everyday terms, it resembles a pot of dense soup kept just below boiling, where movement never fully stops, even without stirring. This molten surface also influences the planet's atmosphere. As lava heats, elements evaporate directly from the rock. Sodium, silicon-based compounds, and oxygen can briefly exist as vapor above the surface. These materials do not form clouds or weather systems. They are quickly dispersed by radiation from the nearby sun, leaving behind a constantly renewed but unstable envelope. Observations using infrared light support this picture. Changes in thermal emission suggest a surface capable of absorbing and releasing large amounts of heat. Unlike reflective clouds or ice, molten rock stores energy efficiently. This helps explain why temperature differences between regions may be smaller than expected despite permanent day and night. The lava oceans of 55 Cancri E connect the planet's interior to its environment. Heat generated deep within the planet rises through molten layers and escapes at the surface. The planet does not burn violently or collapse. It maintains a steady balance of melting, flow, and radiation. These oceans are not signs of destruction, but of equilibrium under extreme conditions, shaped by physics rather than instability. The atmosphere of 55 Cancri E exists in a constant state of stress. Unlike Earth, where air circulates gently between warm and cool regions, this planet experiences extreme temperature contrasts driven by its locked rotation. Energy arrives continuously on the day side and must be redistributed without the help of oceans, clouds, or stable weather systems. As the surface heats, vaporized material rises rapidly. Even thin layers of gas respond strongly to temperature differences. Hot regions expand, cooler regions contract, and pressure gradients form almost instantly. These gradients drive powerful winds that race across the planet's surface. Models suggest that these flows can reach speeds far exceeding those of Earth's strongest storms. The composition of these winds is unusual. Instead of nitrogen or oxygen, they likely carry vaporized rock and metal compounds. Sodium and silicon-based molecules move with the flow, glowing faintly as they absorb and release energy. In everyday terms, it resembles heat shimmering above asphalt on a hot day, but extended across an entire hemisphere and sustained without pause. Thermal stress shapes the surface beneath these winds. Materials expand when heated and contract when cooled. On 55 Cancri E, this process occurs continuously near the boundary between day and night. Rock is subjected to repeated strain, weakening its structure and encouraging fracture and flow. Solid ground never fully stabilizes. These forces do not create chaos in the way explosions do. Instead, they establish a harsh but predictable pattern. Heat drives motion. Motion redistributes energy. Radiation strips material away. The system repeats without interruption, guided by physical laws rather than chance. The result is a planet where motion never rests. Winds, heat, and pressure remain locked together in a cycle that defines the environment. This constant movement is not a sign of instability, but of balance under extreme conditions. On 55 Cancri E, even the air reflects the planet's defining trait: relentless energy shaped into steady flow. The absence of a normal day and night cycle on 55 Cancri E is not a coincidence. It is the result of a process known as tidal locking. This occurs when a planet orbits so close to its star that gravitational forces gradually slow its rotation. Over time, the same side of the planet comes to face the star at all times. On Earth, tidal locking is visible in a familiar example. The moon always shows the same face as it orbits our planet. On 55 Cancri E, the effect is far more extreme. The distance to its star is so small that tidal forces acted quickly, reshaping the planet's rotation early in its history. This locked state removes the alternating rhythm that shapes most planetary environments. One hemisphere receives constant radiation, while the opposite side remains permanently shielded. The day side absorbs energy continuously, driving melting, vaporization, and atmospheric motion. The night side, lacking direct heat, remains comparatively cooler, though still far from cold by Earth standards. The boundary between these two regions plays a critical role. Near this dividing line, known as the terminator, temperatures shift rapidly. Material experiences repeated expansion and contraction as it moves across this zone. Heat-driven winds transport energy from the day side toward the night side, attempting to balance the difference. Despite this transfer, equilibrium is never fully reached. The planet does not rotate fast enough to distribute heat evenly. Instead, it settles into a stable imbalance. Permanent day and permanent night coexist, each defining the other. This configuration explains many of the planet's features, from lava oceans to high-speed winds. Tidal locking is not a rare outcome in the universe. Many planets orbiting close to their stars share this fate. On 55 Cancri E, it serves as the structural foundation for every surface and atmospheric process observed. Without a turning sky or passing night, the planet remains fixed in its orientation, shaped by gravity into a world where time moves forward, but the sun never shifts its place. For a long time, rocky planets were understood through a single template. Earth, Mars, Venus, and Mercury shaped the definition. These worlds are built primarily from silicate rock and metal, with compositions dominated by oxygen and silicon. When astronomers spoke of rocky planets, they implicitly meant planets that followed this familiar pattern. 55 Cancri E challenges that assumption. Its mass, size, and density place it firmly within the category of rocky planets, yet its internal chemistry appears fundamentally different. The planet demonstrates that being rocky does not require Earth-like minerals. Solid worlds can emerge from alternative chemical pathways, producing structures unfamiliar to our experience. This realization comes from combining planetary measurements with stellar chemistry. The host star's composition influences the materials available during planet formation. In systems where carbon is abundant relative to oxygen, carbon-based solids form more readily than silicas. As these solids accumulate, they create planets that are dense and rocky, but not Earth-like in structure. An everyday comparison helps clarify this shift. Two houses can be built to the same size and weight, yet one may be made of concrete while the other is built from wood and steel. Both are solid structures, but their internal properties, behavior under stress, and long-term durability differ. In the same way, 55 Cancri E occupies the rocky category while redefining what that category includes. This expanded view has practical consequences for astronomy. When scientists detect a dense exoplanet, density alone no longer guarantees an Earth-like composition. Rocky planets may hide carbon interiors, exotic mantles, or unfamiliar mineral layers. Classification becomes less about resemblance and more about formation history. By existing as it does, 55 Cancri E quietly reshapes planetary science. It shows that Earth is not the default outcome of rocky planet formation, but one option among many. The term rocky planet now carries broader meaning, encompassing worlds shaped by chemistry as much as by mass and size. Life on Earth is built around a specific chemical foundation. Oxygen bonds readily with many elements, forming water, silicate rocks, and the molecules essential to biology. This oxygen-rich chemistry shapes everything from the air we breathe to the structure of continents. It is so familiar that it often feels universal. 55 Cancri E represents a different chemical outcome. In its region of formation, carbon was more abundant relative to oxygen, When this balance shifts, chemistry follows a new path. Carbon begins bonding with itself rather than combining primarily with oxygen. The result is a world where familiar Earth materials are no longer dominant. On Earth, carbon plays a supporting role. It forms the backbone of living molecules, but it does so in small quantities within a vast oxygen-based environment. On a carbon-rich planet, carbon becomes structural. Instead of appearing mainly in life or fuel, it may form large-scale layers of graphite, carbide minerals, and diamond-like material. An everyday analogy helps clarify the contrast. Cooking changes dramatically depending on which ingredient is most abundant. A kitchen filled mainly with flour produces bread and pasta. A kitchen dominated by sugar produces sweets. The tools are similar, but the outcomes differ. In planetary terms, the same elements follow different rules depending on what is available in excess. This chemical difference has consequences for habitability. Oxygen-rich environments allow water to remain stable across a wide range of temperatures, supporting complex chemistry. Carbon-dominated worlds struggle to maintain liquid water and stable atmospheres. Even when carbon is plentiful, the pathways that lead to life as we know it become unlikely. By comparing 55 Cancri E to Earth, scientists refine their understanding of life's limits. The planet shows that chemistry sets boundaries before biology ever begins. Earth's environment is not just rare because of its location, but because of a precise balance between elements. In the wider universe, carbon and oxygen arrange themselves in many ways, and only a narrow range produces worlds like our own. Human civilization assigns value through use, scarcity, and context. Gold is valuable because it is rare and durable. Water is valuable because life depends on it. These judgments feel natural on Earth, where environments are stable enough for ownership, trade, and long-term planning. Value, in this sense, is a social agreement supported by physical conditions. On 55 Cancri E, those conditions do not exist. The planet's surface remains hot enough to melt rock. There is no stable ground, no breathable air, and no region where materials can be stored or preserved. Even if diamond-like structures are abundant beneath the surface, they cannot be accessed, transported, or used. In practical terms, ownership becomes impossible. An everyday comparison makes this clearer. A vault filled with priceless artifacts has meaning only if it can be entered and protected. If the vault sits at the bottom of an active furnace, the contents lose their relevance. The materials remain, but the concept of wealth collapses because interaction is no longer possible. This highlights a deeper point about civilization. Economic value is not an inherent property of matter. It emerges when environments allow stability, repetition, and trust. Earth provides these conditions through moderate temperatures, predictable cycles, and accessible resources. On 55 Cancri E, constant heat and radiation prevent such systems from forming. The planet therefore acts as a natural counterexample to human intuition. Abundance does not guarantee usefulness. Rarity does not guarantee importance. Without the ability to interact safely and consistently, materials remain inert from a cultural perspective. By examining worlds like 55 Cancri E, scientists and philosophers alike are reminded that wealth is local. It depends on where you are, not what exists. The planet holds immense quantities of familiar elements, yet offers nothing that civilization could use. In this contrast, the limits of human-centered value systems become clear, framed by physics rather than opinion. The discovery of 55 Cancri E has influenced more than curiosity about exotic worlds. It has reshaped how scientists think about planet formation itself. For much of modern astronomy, planetary models were built around the solar system. Rocky planets were expected to form close to stars, gas giants farther out, all following a similar chemical recipe. As more exoplanets were discovered, this orderly picture began to blur. 55 Cancri E contributed a crucial piece to that shift. Its density and composition could not be explained by standard Earth-like models. This forced researchers to revisit assumptions about the materials available during planet formation. Planets form from disks of gas and dust surrounding young stars. The exact chemical balance of these disks determines what solids condense first. In oxygen-rich disks, silicate minerals dominate. In carbon-rich disks, different solids emerge. 55 Cancri E likely formed where carbon compounds condensed efficiently, altering the planet's internal structure from the very beginning. Migration also plays a role. Evidence suggests that 55 Cancri E did not necessarily form in its current orbit. Interactions with the disk and neighboring planets may have drawn it inward over time. This process exposes planets to new environments after formation, reshaping surfaces without altering their cause. An everyday comparison helps clarify this idea. A metal object forged in one factory can later be moved into a furnace or freezer. Its surface changes, but its internal composition remains tied to where it was made. In the same way, 55 Cancri E carries the chemical signature of its birthplace, even as its orbit transformed. By accounting for chemistry, migration, and timing, planet formation becomes less predictable and more diverse. 55 Cancri E stands as evidence that planetary outcomes depend on subtle initial conditions. Rather than following a single blueprint, planets emerge from a wide range of pathways, each shaped by the environment in which they be. When considering life beyond Earth, it is tempting to focus on the presence of familiar elements. Carbon, heat, and geological activity are often associated with biological potential. On 55 Cancri E, these ingredients exist in abundance, yet life, as understood through Earth's example, requires more than raw materials. One essential factor is stability. Life depends on environments that remain within certain limits for long periods of time. On Earth, liquid water persists because temperature and pressure fluctuate within a narrow range. On 55 Cancri E, conditions exceed those limits continuously. Surface temperatures remain high enough to melt rock, preventing the long-term presence of liquid water in any stable form. Another requirement is chemical balance. Biological processes rely on controlled reactions, where molecules can assemble, break apart, and reassemble predictably. Extreme heat accelerates reactions beyond control. On this planet, molecular structures would be disrupted faster than they could organize. Carbon, while abundant, becomes locked into rigid crystal forms or vaporized states, rather than flexible biological chains. Atmospheric conditions further limit possibility. A stable atmosphere protects developing chemistry from radiation and helps regulate temperature. On 55 Cancri E, intense stellar radiation strips away gases almost as quickly as they appear. Any temporary atmosphere formed from vaporized rock lacks the thickness and consistency needed to shield or sustain complex reactions. An everyday comparison helps clarify this limitation. Ingredients alone do not produce a meal. A kitchen also needs controlled heat, time, and tools. Too much heat burns everything instantly. On this planet, the heat never lowers enough for delicate processes to proceed. The absence of life on 55 Cancri E is not a failure of possibility, but a result of boundaries set by physics. Life requires balance more than abundance. This world demonstrates that even with familiar elements present, the conditions that allow biology to emerge are narrow. In understanding where life cannot exist, scientists refine their understanding of where it can. When 55 Cancri E was first described, it appeared exceptional. A dense, carbon-rich world so close to its star seemed like a rare accident. As exoplanet surveys expanded, that impression began to change. Astronomers now recognize that the conditions required to form such planets are not unique to a single system. Carbon-rich environments arise naturally during star formation. In certain regions of protoplanetary disks, carbon-bearing compounds condense efficiently, while oxygen becomes locked away in other forms. When this balance persists, solid material rich in carbon accumulates. Planets forming in these zones inherit that chemistry from the start. Statistical studies of stars show wide variation in elemental ratios. Some stars resemble the Sun, while others contain significantly higher carbon to oxygen proportions. Each of these stars hosts its own planetary disk, shaped by local chemistry and temperature. Over many systems, this diversity increases the likelihood of carbon-dominated rocky planets forming. Orbital migration further expands their presence. Planets do not always remain where they form. Interactions within the disk can draw solid worlds inward toward their stars. As a result, carbon-rich planets that originated farther out may later appear as hot, dense worlds, similar to 55 Cancri E. An everyday comparison helps place this in context. A single unusual building may seem rare until a city map reveals entire districts built from the same materials. The first example draws attention, but the pattern becomes clear only with broader perspective. Current observations suggest that worlds like 55 Cancri E are not common in absolute terms, but neither are they singular. They represent one outcome among many in planetary formation. As detection methods improve, more carbon-rich rocky planets are likely to be identified. Each discovery shifts perception further away from Earth-centered expectations and toward a universe where planetary diversity is the rule rather than the exception. When discussing planets like 55 Cancri E, the language of value often reappears. Words such as rare, precious, and valuable slip easily into descriptions. These terms work well on Earth, where resources are limited by access and environment. At a cosmic scale, however, the meaning of value begins to thin. The universe contains an immense quantity of matter. Carbon, silicon, iron, and oxygen are produced in large numbers by stars over long periods of time. Supernova explosions spread these elements across galaxies, seeding new systems again and again. What feels scarce within one planetary system may be abundant when viewed across billions of stars. Scale changes interpretation. A diamond on Earth is valuable because it is difficult to form and harder to extract. In space, the same atomic structure can arise wherever pressure and chemistry allow. The universe does not conserve materials for usefulness. It produces them wherever physical conditions permit, without preference. An everyday comparison helps clarify this shift. A drop of clean water is precious in a desert, but unremarkable beside a river. The substance does not change. Only the surrounding context does. In the same way, Diamonds gain meaning on Earth because of limitation, not because of their intrinsic nature. At cosmic scale, abundance overwhelms attachment. Entire planets can be rich in materials that would reshape economies on Earth, yet remain completely irrelevant to life or civilization. Distance, heat, and radiation turn potential wealth into unreachable matter. 55 Cancri E illustrates this perspective quietly. It does not diminish Earth by comparison. Instead, it reframes how value arises. The universe provides material freely and repeatedly. Meaning emerges only where conditions allow interaction, continuity, and need. Beyond those boundaries, matter exists without significance, shaped by physics alone. Rarity often attracts attention. In human experience, what is uncommon is frequently treated as important. Rare minerals, rare animals, and rare events gain significance simply because they stand apart. This instinct works well on Earth, where ecosystems and resources are limited by space and time. In the universe, rarity follows different rules. A phenomenon may be rare within a single planetary system, yet common across many others. A planet like 55 Cancri E might appear unusual when compared only to Earth, but that comparison narrows perspective. When thousands of star systems are considered together, patterns emerge that soften the meaning of rarity. Astronomy repeatedly reveals this effect. Hot Jupiters were once considered strange because the solar system lacks them. As more planets were discovered, they became recognized as a frequent outcome of planetary migration. What changed was not the planets themselves, but the reference frame used to judge them. An everyday example helps ground this idea. Snow feels rare in tropical regions and ordinary in polar ones. The substance does not change. Importance shifts with location and expectation. In the same way, a carbon-rich rocky planet may feel exceptional only because Earth occupies a narrow category. Importance in science is not assigned by scarcity alone. It emerges from what a discovery explains, clarifies, or challenges. 55 Cancri E matters because it expands understanding of planetary chemistry and formation, not because it contains unusual material. By separating rarity from importance, scientists avoid misleading conclusions. Some rare objects teach little. Some common ones reveal fundamental rules. 55 Cancri E earns attention not through novelty, but through the way it reframes assumptions. In this distinction, the universe appears less like a collection of curiosities and more like a system governed by consistent, discoverable principles. Human understanding of the universe begins from a single reference point. Earth provides the baseline for temperature, chemistry, time, and scale. From this position, other worlds are compared, labeled, and judged. This approach is practical, but it quietly shapes perception. 55 Cancri E exposes the limits of that perspective. Its environment does not align with terrestrial expectations. Day and night do not alternate. Solid ground does not remain solid. Familiar materials behave in unfamiliar ways. When Earth-centered assumptions are applied, the planet appears extreme or unnatural. When those assumptions are removed, it becomes a logical outcome of known physical processes. Astronomy repeatedly encounters this shift. Early models of the universe placed Earth at the center. Later, the Sun took that position. Each transition required letting go of comfortable frames of reference. Exoplanet research continues this process. revealing that Earth-like conditions occupy a narrow region within a much broader range of planetary states. An everyday example helps clarify this adjustment. A person raised near the ocean may find a desert difficult to imagine as habitable. To someone accustomed to arid environments, the desert is structured, predictable, and livable. Neither perception is wrong. Each reflects the environment that shaped it. 55 Cancri E functions as a mirror rather than an anomaly. It reflects the assumptions carried into observation. The planet does not challenge physics. It challenges expectation. By studying such worlds, astronomers learn to separate universal laws from local experience. This shift in perspective does not reduce Earth's significance. Instead, it sharpens it. Earth becomes one expression among many, not the default template. Through planets like 55 Cancri E, the universe is understood less as a variation of home and more as a landscape of outcomes, shaped by consistent rules acting on diverse conditions. Across the vast range of planetary outcomes, Earth occupies a narrow and delicate position. Its surface temperatures allow water to remain liquid. Its atmosphere shields life from radiation while permitting light to pass through. Its chemistry supports complex reactions without overwhelming them. These conditions are not dramatic. They are precise. When viewed alongside worlds like 55 Cancri E, Earth's value becomes clearer through contrast rather than comparison. Earth is not defined by abundance of rare materials or by extreme forces. It is defined by balance. Heat arrives, but not too quickly. Energy escapes, but not too freely. Matter circulates without locking into permanent extremes. Fragility often carries a negative meaning. In planetary terms, fragility describes sensitivity to change. Small shifts in distance, composition, or rotation could alter Earth's environment completely. Yet this sensitivity is what allows complexity to exist. Stability emerges not from rigidity, but from controlled variation. An everyday analogy helps ground this idea. A finely tuned instrument produces sound only when tension is exact. Too loose, and nothing resonates. Too tight, and the string snaps. Earth functions in a similar way. Its systems respond gently to change without collapsing into chaos or stagnation. Planets like 55 Cancri E highlight this condition by absence. They show what happens when balance is lost to excess heat, pressure, or proximity. These worlds are not failures. They represent outcomes shaped by physics acting under different parameters. In this wider context, Earth's significance does not come from rarity alone. It comes from the narrow range of conditions that allow persistence, interaction, and continuity. The universe produces many kinds of planets. Only a small fraction remain quietly suitable for life. This subtle suitability, more than any material wealth, defines Earth's true value.